So here I am sitting in a Scratch directory, and it should be empty. Yep. So this is where we're going to work on our Unison program, and we're going to do that in two windows. The first is where we're going to run something called UCM, which is the Unison Code Manager, and that's the thing which is basically like a kind of background IDE. And then we're going to run an editor in the other window, which is where we're going to create code. So let's split the screen here. Okay, and over here, I'm going to run UCM, the Unison Code Manager. And we have the nice little rainbow logo there. And the important thing down here, I'm watching for changes to .u files in that directory that I'm in, Dave Scratch. So this is monitoring that directory for any changes to any Unison source files. Now, before I start typing Unison source code, it's good practice to put your code into a namespace. And in this case, I'm just going to create a namespace called magic. And as it says, the magic namespace is empty. There's nothing in there. And I need to include all of the Unison standard libraries in my namespace to make it accessible. This sounds like a bit of a crazy thing to have to do, but what it really means is I'm currently going to freeze the version of all the standard libraries to whatever they are right now. And it will stay that way even if the standard libraries change. Now, I can always update it later on, but for now, I'm just going to fork the standard library, which is .base, and the convention is that goes into something called libbase. So now if I list this namespace, I now have a lib, and if I go into lib, you see this base, and if I do lib, then I have all of the standard library for Unison. Okay, so let's clear the screen here. Back over in our terminal on the other side, the left-hand side, I am going to go into my editor and I'm going to create a file. It doesn't matter what it's called because we're not going to use it apart from as a way of communicating with UCM. And it's got to end in .u because it's a Unison file. So I'm editing. I'm going to create a function called add, and add is going to take two natural numbers, and add them together. Unison, like Haskell, allows me to do type signatures. You don't always have to do them because most of the time you can actually infer what the types are. Add is a bit special because it could be a natural number, an integer, or a float. And so rather than have to sit there and disambiguate it, I'm actually going to give it a type signature. So a type signature is going to look add. It takes a natural number and another natural number, and it returns a natural number. If you haven't seen this style of type signature before, it's common in functional languages that do currying, and what it really says is that the very last type is the return type, and the types before that you can consider to be the types of the function we're defining. So our function add takes two parameters, and it simply returns a plus b. Now, it's nice to be able to test that, and Unison has a very nice feature called watch expressions. So in my case, I just want to call add, say 3 and 4. So now if you watch the UCM window, that's the right-hand window, when I save this file away, interesting. I found and type checked these definitions in t.u, and sure enough, there's our add function. And then I'm evaluating any watch expressions, and you can see here, it adds 3 and 4, and the result is 7. So we could stop at this point, but this is a bit like printf debugging. I would much rather have a test. To make this into a test, I just have to put a test to the left-hand side of that greater than. Now, optionally, I'll give the test a name, and it's always good to do that because it's easier to keep track of what's going on. So we'll call this test add.test. And it's going to have an assertion which in Unison is check. So we're going to check that add 3 and 4 equals 7. So then we save that away. And notice that we now have defined two functions, add and add.test, and our test passed. It said that it actually proved it, but most importantly, we have a little green check mark there. If we made our test fail, so if we make that 8 instead, then we get the little no entry sign of failure. So we'll go back and fix that. Save that again one last time. And we have a passing test. Now, I found and type checked these definitions in scratch.u. That's these two functions. If you do an add, then this is what your code, this is how your code base would change. And it would add these two functions. So right now, those functions are inside UCM's memory, but they're not stored in my code repository. But if I say add, now they are. And they have been stored in a repository somewhere on my machine and a database. I really don't care. I can now go back over to my file here. Let's come back out to the terminal. And we're going to remove that source file. And come back in and edit. So you see it's totally blank. Now, maybe I made a mistake and I need to change my function. And you just saw me delete the source. No, that's not a problem, because I can say edit add. That's the name of the function. And back over in my source file now, you'll see that my function's back again. Now, it's actually slightly different. You see it's got this use nat plus, but that's because it doesn't actually store my source code in the repository. What it's storing is the logical function, the AST for this function, and then it reconstitutes it when it brings it back out again. And so I could make changes here if I wanted to, and then save them back. I don't need to do that. So let's just delete that buffer. And let's define a function called square. And we know how to do that now. Square takes a natural number and returns a natural number. And square A equals A times A. And we'll do a quick test. Okay, save that away. And again, look over in the UCM window on the right there. And now we've added two new functions, square and square.test, and our test passes. Cool. So let's add that to the repository. And if I list the repository now, you'll see that I got that lib that I created initially. Remember, that's got the standard library in it. Then I have add, and then basically a subdirectory or a sub namespace for the add test, and then square and square test goes in there. Okay, so back over here in our editor, we're going to do the same thing again, delete the file, and this time I'm going to write a function that sums the squares of two numbers. So sum square is going to take a natural number and another natural number. Those are the two parameters, and it's going to return the sum of their squares, also a natural number. So the sum of the squares of A and B are add. We already defined our square function, A and square B. And again, we can write a quick little test for that. So sum square dot test equals check. Let's do a 3, 4, 5 triangle. Excellent. So let's see what happens there. Yay, that test passed. So we'll pop over and we will add that into our repository as well. And if we do ls now, we now have square, sum square, and add, and we can run all tests. And we have 3 tests passing. That's great. So clear the screen here. Now, if we have a look at our functions that we defined so far, something's a little bit ugly here in that I have sum square, which is correct. I mean, you call it the sum of two squares. But then the function that actually does the summing, I called add, and that's not so good. So what I'd really like to do is to rename that function, and I can do rename term add to be sum. And I've still got that add there for the test. So I'm going to do a rename term add.test to be sum.test. Okay, so now we've renamed our two functions. What happens if we run our tests? Now, at this point, you might be expecting them to fail because sum square is actually still using add, and yet we renamed add to be sum. Nope, all the tests pass. Now, why is that? Well, we can use UCM to look at the source code of sum square. And look here. That's changed to be sum. Now, you might be thinking, when you rename a term, Unison goes through all the source code and updates it so that add becomes sum. And that would be neat on its own, but that's actually not what happens. What happens is actually far cooler than that. All right, so we finished for the day, and we're going to come out of this, and we're going to come out of our editor. And we're going to remove that t.u file again, because we don't need it. So a couple of months later, we're going to keep working a little bit on our project here. So I'm going to bring up the UCM and go back into our magic namespace. And then back over here, I'm going to edit a file just to make it different. I'm going to call this fred.u. And for some reason, I need a function that adds 3 numbers together. And I'm just going to call it sum because I'm lazy. So the type signature is going to be sum net. And I'm going to say sum A, B, B, C equals A plus B plus C. And of course we test it. Okay, so we'll save that away. And over here, we definitely have a function called sum3.test, and 1 plus 2 plus 3 does equal 6. And look at this. Here it says that it's type checked these definitions. This one is okay to add, sum3.test, but this name already existed. And what I'm about to do is to overwrite my sum function with my one that does 3. Is that a problem? Let's find out. I'm actually going to save both of those away. So I'm going to do update to add the sum function and add to add its test. And we'll have a look to see what happens when we run the overall tests. So the wild thing is that the sum square test still passes, even though I have changed the definition of sum. So what's going on here? Let's have a look at the source of sum square. And look at this. Where we used to have sum, we now have this weird string, hash AUT6, blah, blah, blah. And somehow that means sum. Well, if we assume that that's a function, I can copy that and actually say, let's view what that is. And there we go. Hash AUT6, whatever, is our original sum that adds 2 numbers together. And we now have this new one, which adds 3. So somehow Unison kept the old definition lying around, and it's called this AUT6 thing. And because we updated sum, the word sum no longer, or the name sum no longer refers to that old function, but it's still got it under this AUT name. So here's a strange thing. If I go back into my editor buffer, delete it again, and let's create a function that looks the same as our original sum. Let's call it, total. And it also takes a natural, and it returns a natural. And we'll define total, and it takes 2 parameters, and its return value is addEnd1 plus addEnd2. All right, save that away. And sure enough, we've now created a function called total that does our addition. We'll add that into our code base. Now let's have a look at sum square. Look at that. It's noticed that the total function does the same thing as our original sum function. And so it decided that I may as well not use this weird name anymore. I'll just use total because it does exactly what I want. So how on earth does it do that? Well, let's have a look. We created our initial add function with the spec, natural goes to natural goes to natural, and the implementation. So add AB goes to A plus B. And we distinguished between the name that we were binding to that function and the function itself. The function definition in a functional language is just another value, just like a natural number or a float or a string. And then we bind it to a name, in this case, add. And of course, being a functional language, we can pass that function to other functions. Internally, the compiler is likely taking our source code and, at least at some part of the process, converting that into an abstract syntax tree, something that represents the function. So here you can see that the add is going through an equals node, which I'm using for binding, and then we have the function definition. And the function definition really encapsulates what that function does, right? It's the AST of the function implementation. It includes the parameters and the body. And because it's an AST, it is just a data structure. Because it's a data structure, it can be hashed. And in fact, if we hash it in Unison at least, we end up with this hash AUT6J, whatever it was, number. And that is a 512-bit hash of the function implementation, of the function AST. And that uniquely identifies every function that has that AST. They all have the same hash. Just to reiterate that hash uniquely identifies every function of the form parameter 1, parameter 2 equals parameter 1 plus parameter 2. Doesn't matter if it's AB equals A plus B or XY equals X plus Y, or as we saw, addend 1, addend 2, or some arbitrary number of parentheses, assuming the AST strips them back down to the base form. So any function we write that adds two numbers that looks like this will have that same hash, AUT6J whatever. Internally, when UCM stores our function into the repository, it's actually going to store three things. It's going to store the AST, because that's how it knows what to run. It's going to index that AST using our hash, and you can think of that as the internal name. And I say secret there because it doesn't necessarily get revealed. It's not really that secret. You can find it out very easily. And then we have one or more aliases to that particular secret name. So on the outside, I can refer to add, and internally, it knows that means hash AUT, which in turn means that particular piece of AST. So now we can define our sum square function. And again, the function part of that definition is an AST. And we can look at that AST. It's a function definition with two parameters, just like the add one was. But the interesting thing here is we are using the function sum. But if you look at what's actually stored in the AST as the name of that function, it is not sum. During the compilation process, it's going to look sum up in the repository. It's going to find that that's an alias for that hash AUT name, and that's the name it's going to use in the AST for sum square. And it will do the same things for our square functions further on as well. So at the end of this, we now have at least two functions stored in our repository, add, which we've already seen, and sum square, which has got a totally different hash. And again, notice it has the AUT, so that when we actually execute sum square, it's going to go through this, it's going to find that reference to AUT6J, it's going to look it up, and then find the actual body for that function. Then we thought, okay, we're going to fool it. We're going to create a new version of sum that has three parameters. So sum that adds A, B, and C to produce A plus B plus C. This has got an AST, which is different to the original sum. And so it's going to have a different hash. So it has the hash R40H, and we've told it to alias sum to that original hash. That means sum no longer points to our first hash, the AUT hash. It now points down to R40. But inside sum square, the AST is still referencing the hash, the AUT number. So when we execute sum square, it's actually going to run that original function. Even though it doesn't have an external name or an alias name, it's still going to be able to run that function because the function is never destroyed. It is always available and it is always referenced via that hash, the AUT hash. So in Unison, all of our code is stored in a repository and all of that code is immutable. And because the hash value is derived from that code, the hash value is also immutable. And the two of them will always refer to each other. All references to the code that we run is done using that hash. So as we compile the code, we're going to convert all of those alias names into hash names. And because that hash is immutable and the code it refers to is immutable, that code will always use that version of the function. Even if we were to delete it from the outside, it is still there in our repository and it still has that same name, that same hash. And that's going to apply to everything, not just the code that we write, but all of the code that other people write and all of the code that forms part of the Unison libraries. Everything has this hash name that refers to some immutable chunk of code. So when we edit our code, UCM is going to replace the names in that code with hashes, and it's going to store those functions into the repository. And that repository could be local, it could be distributed, it doesn't really matter. When we run the code, effectively what we're doing is running a function, which means we're running a hash, and it's going to go fetch that function based on that hash, and it's going to start executing it. As it does so, it's going to be fetching other dependencies if necessary. Whether it does that immediately or whether it does it as it's running, irrelevant. So what does this mean to us? Well, during development, we are going to be editing our code and we're going to be using other people's functions and libraries, and we're going to be using UCM as our coding environment. The source code that we create is ephemeral. The only thing that gets stored is the ASTs and the names that get stored into the repository. That's a bit scary, but it has some really big upsides. In particular, we don't need a package manager, we don't need a build tool, and we don't need separate version control, because it's all provided as part of the language. Maintenance. Well, here's the cool thing. If you've ever dealt with a project which is a year old and you go and refetch the dependencies, and of course it doesn't work, and you've got to go through and work out what's changed, well, with Unison, that doesn't matter. By default, your existing code will always run because it's always have access to the state of the universe at the time you last compiled it and ran it. If you need to, you can manage updates. So if someone's updated a library that you use and you want to use that update, you can tell Unison to start merging those updates into your local version of that library. UCM has got an amazing amount of support for this version management. It's like a mini version of Git, but for code. And then the cool thing is, and this is where I'm going out on a limb because really we haven't quite worked out how this is going to work in practice. But for deployment, fundamentally all you have to do is to send a function's hash to some remote machine's version of UCM. And from there, the function should just be able to run. Now, obviously we have more packaging involved, particularly if we have credentials and this kind of thing that we have to pass back and forth. But in theory, right, all that's needed to deploy our app is a function hash. And we can pass that as many times as we want to as many different servers as we want if we want to get it running. And as we'll see in the third part of this series, Unison has some really, really cool ways of distributing code. So I hope what I've done is shown you that immutable code actually isn't as crazy an idea as it sounds, and it actually has some really big benefits. Keep an eye on it.